Let's explore the constant and the power rules. What I mean by the constant rule is let's consider the constant function f of x equals c for any real number c. Then the derivative function f prime of x is going to be the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. And the nice thing about this is f of x is a constant function. So when we're trying to find f of x plus delta x, it's going to be c, and f of x is c. So when we simplify this fraction, we get the limit as delta x approaches 0 of 0 over delta x, which is 0. So what we just showed for our constant rule is that if we wanted to find the derivative of a constant, it will always be 0. And when we think about that in terms of the tangent line, it should make sense. I mean, a constant function, if we were to graph it, looks like a horizontal line with a y-intercept of c, whatever c is. And for any point on this line, what's going to be the slope of a tangent line? Well, what would the tangent line look like? It would look like the horizontal line running through that point. And so the slope of that tangent line is going to be 0. No matter where that horizontal line is, the slope is always 0. So our derivative is always 0. And that's what we call the constant rule. As for the power rule, let's let f of x equal x to the n for any integer n. Then f prime of x, again, we're going to use that delta x definition, so the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. So we do a little substituting. Got to keep my limit notation around. Haven't taken the limit yet. Haven't done anything with my denominator, so I have to keep that around. But f of x plus delta x is going to be x plus delta x to the nth power. And we subtract off f of x, which is x to the nth power. Now we have to do the expansion. And that gets a little bit lengthy if you remember the binomial theorem. Let's see, I gotta keep my limit around, got to keep my denominator around, but x plus delta x to the nth power starts off with n choose 0, which is 1, times x to the nth times delta x to the n minus n, which is just 0. The next term is going to be n choose 1, which is n, times x to the n minus 1 times delta x to the first. And then we go to the next term is going to be n choose 2 times x to the n minus 2 times delta x to the second. And that's going to continue until we get down to n choose n, which is 1, x to the n minus n, which is x to the 0, and then delta x to the n. But that's the entire expansion of x plus delta x to the nth power. We still have to subtract off x to the n. So our fraction bar goes a little bit further. Now we go through and start canceling. We do have a little bit of canceling that can happen because 1 times x to the n times delta x to the 0, that's just x to the n, which cancels with this x to the n as well. And every term that's left over is going to have a delta x in it, at least one. So I'm going to factor that delta x out of every term. I still have to keep my limit notation around. Haven't taken the limit yet. Still have to keep my denominator around as well. But I'm going to factor out that delta x out of every term. And as we go through term by term, first we have n times x to the n minus 1 times delta x. Take that delta x out. We're left with n times x to the n minus 1. The next term, n choose 2, x to the n minus 2. But it says delta x squared. We're taking one of them out, and so we're just left with delta x. And this pattern will continue all the way to the end. 1 times x to the 0, that's also 1. So I have that delta x to the n. I'm going to take one of those out, and we'll have just n minus 1 power left. All right, a little bit of canceling again. Now we do get rid of our denominator, and we're ready to take a look at the limit. We'll have n times x to the n minus 1, n choose 2, x to the n minus 2, delta x. The next term would actually be n choose 3, x to the n minus 3, and then delta x squared. But that's going to continue all the way down until we get to delta x to the n minus 1. And the thing is, all those delta x's are turning into zeros. So this term has a delta x in it, so does this term, so does every term all the way down to the end. All of those turn into zeros, so we're only left with this part, n times x to the n minus 1. So overall, what we just showed is the derivative of x to the nth power is going to be n times x to the n minus 1. So what was the old power has now become the coefficient, and the power is decreased by 1. That's what we call the power rule. Now, knowing these two rules makes finding derivatives a lot easier. I mean, think about this. If we wanted to find f prime of x, we'd have to take limit as delta x approaches 0 of x plus delta x to the 7th power minus x to the 7th all over delta x. All right. Now, do you want to expand x plus delta x to the 7th power? I don't really want to do that either. Instead, we can just find f prime of x by bringing the power down as a coefficient and then reducing the power by 1. So 7x to the 6th. For g of x, want to find the derivative of g of x? G of x is constant. So derivative of all constants is 0. For h of x equals 1 over x to the 5th. Well, think about that as x to the negative 5th power. Then we can use our power rule. The derivative is going to be bring the power down, so negative 5 is a coefficient, and reduce the power by 1. So negative 5 minus 1 is negative 6. And this even works when we have rational powers as well. That if I wanted to find this derivative, I would first think about the square root of x as being x to the 1/2 power, bring the power down as a coefficient, and then reduce the power by 1. So 1/2 minus 1 is negative 1/2. If you wanted to rewrite that as a radical, that would be 1 over 2 square root of x. And we've been using the derivative to write the equation of tangent lines. So let's find the equation of line tangent to y equals x to the 3rd when x is 4. Remember, we need two things in order to find the equation of line. We need a point. I got the point when my x-coordinate is 4, and the y-coordinate is going to be x cubed. So that's 64. Now, since I'm trying to find the derivative at this specific point, we used to have to do this. We used to have to find the derivative of x to the 3rd evaluated at x equals 4 by using the limit as x approaches 4 of x minus 64 over x minus 4. Right? And we had to break that into its factors and cancel and all sorts of stuff. But now we can find the derivative of x cubed by using the power rule. We bring the power down and reduce the power by 1. Now, when I want to find the slope of the tangent line, I'm just going to find that derivative evaluated at 4. So we'll have 3 times 4 squared. 3 times 16 is 48. There's our slope. Over here is our point. So when we put those two together, the equation of our line is y minus the y-coordinate is equal to slope times x minus the x-coordinate. And there's our tangent line. All right, let's try one more. Find the equation line tangent to y equals x square root of x when x is 5. So for our point, the x-coordinate is going to be 5, and the y-coordinate is going to be 5 square root of 5. In order to find the slope of our tangent line, we're going to need the derivative. But before I find y prime, I want to look at y, since we have x times the square root of x. That's going to be x times x to the 1/2 power, which is just x to the 3/2 power. Right? Then we can use the power rule to find our derivative. The derivative of y is going to be bring the power down, so 3/2, and then reduce the power by 1. So 3/2 minus 1 is just x to the 1/2, which would just be 3/2 square root of x. So our slope will be y prime at 5, or 3/2 times the square root of 5. There's our slope. No matter how it looks, it's still our slope. And this is our point. With a point and a slope, we can write the equation of the line, y minus the y-coordinate, 5 root 5, is equal to slope, 3/2 times the square root of 5. And then x minus the x-coordinate. And even though our numbers are now square roots of 5s in there and stuff, that's okay. You know, we still have the equation of our line.